All right, and we are back for another exciting installment of Learning Calculus. So today is something called implicit differentiation. And implicit differentiation comes into play whenever you have something called an implicit function. An implicit function is like this function right up here, where you have both the x and the y, and you don't have like one of them solved for. So like normally we would have this as y equals or something like that. And this is kind of a hard problem to answer. We can't solve for y and differentiate because we know when we take the square root, we would have to have that plus or minus with this y. So it's just not exactly doable here. I will point out that Desmos and GeoGebra, both online graphers, will be able to graph implicit functions like this. So if you want to see what this function looks like, you can go on to Desmos or GeoGebra and graph it, or you can remember from trig precalc when we graphed circles during that home instruction period at the end of the year. This is actually the equation of a circle centered at the origin with a radius of 3. So in order to be able to differentiate this function, what you are going to do is, or this relation I should say, not function, in order to be able to find the derivative of this relation, you will be able to just differentiate throughout everything with respect to x. So that's down here where I see the direction, the strategy is to differentiate both sides WRT x. That means with respect to x. And what does that mean? Well, okay, we are going to dx 9, and we are going to dx x squared plus y squared. All right? So it's just take the derivative of both sides. It's just like whenever we talk about equations. As long as you do something to one side of an equation, you do the same thing to the other side. Now, if I take d dx of 9, you should know that that is 0. You should also know that the derivative of x squared, we're just using the power rule, it is 2x. Now, here's the part that's really confusing. The derivative of y squared, this guy right here. Why is that so confusing? Because we're differentiating it with respect to x, but the variable is a y. So we are going to do this the same way that we would differentiate x squared, but we're going to include a chain on it. So let me show you what that looks like. We're going to have plus, because we have some rule going on here, 2y times the chain. And the chain is going to be the derivative of y with respect to x. So that. The chain is just the derivative of y. Basically what this comes down to when you're trying to do implicit differentiation, differentiate everything. If you're differentiating y, tack on a y prime or dy dx as its chain, and then solve for that dy dx or y prime or whatever you called it. And when I look at this, I've got, let's see, I could subtract 2x from both sides. Subtract 2x. I've got 0 minus 2x gives me negative 2x equals 2y times dy dx. Divide by 2y. Divide by 2y. I now have dy dx is equal to negative x over y. So dy dx is equal to negative x over y. And ultimately, we would probably want to put that as dy dx equals negative x over y instead of how it's ordered over here. All right, you can see on this page, I do actually have a request that you do some practice problems on the companion file. We'll do that tomorrow in class, but really what I wanted to show you here is what happens if you get dy dx in more than one spot. First off, I will point out that I was able to graph this on Desmos just to show you what the graph looks like. And you can see it looks like this. I don't really know anybody who can graph the implicit functions like by hand, but you know, whatever. I'm sure somebody can. So what we're going to do here is we're going to ddx both sides of the equation. So we'll ddx 2y and we'll ddx x squared plus sine of y. And everything is going to be the exact same that we just did. Anytime you take the derivative of y, take the derivative as though it was an x, but then tack on your chain. Again, your chain, you can either put it as y prime or dy dx. Because I think it looks cooler, I'm going to put dy dx. So here, the derivative of 2y. Well, that's a linear. So the derivative is just going to be 2 times the chain. Again, the big idea here, the chain is dy dx. All right? Is equal to the derivative of x squared. Okay, that's just 2x, no chain because we're talking about it's in terms of x. Plus the derivative of sine. The derivative of sine we have is cosine of y times the chain. And the chain, I'm all right with you either putting down dy dx or y prime. Again, I think dy dx looks better. So when we have a situation like this where you get dy dx in more than one spot, what you want to do is you want to collect all the dy dx on one side of the equation and put everything else onto the other side of the equation. So here, I see the easiest way for me to do this is to just take this cosine of y, dy dx, and subtract it to the other side. So I'm going to subtract by cosine of y times dy dx on both sides of the equation, minus cosine of y times dy dx. And all of a sudden, on the left-hand side, I'm going to get 2 times dy dx minus cosine of y times dy dx is equal to just 2x on the other side. And sometimes you'll have to move more than just one term. Basically, we just want dy dx on one side, non-dy dx on the other side. Because now what I can do on the left-hand side, I can factor out dy dx. So I've got dy dx times the quantity of 2 minus cosine of y is equal to 2x. And now to get dy dx by itself, I can divide by 2 minus cosine of y. So the derivative with respect to x is going to be equal to 2x over 2 minus cosine of y. And I am done with that. All right? Whew. So I guess if I wanted to summarize that, I could say take the derivative of everything with respect to x, isolate dy dx, and divide to get it by itself. And this next problem that we have going on here. We have finding the equations of the tangent and the normal to the curve x squared minus xy plus y squared equals 7 at -1, 2. Well, first off, I do actually have what that graph looks like. It looks like this. It looks like the profile of a lens for like fixing your vision. Anybody who wears glasses knows what that looks like. So let me get rid of that. In order to find the equation of the tangent and the normal, all we need to do is find an x value that it goes through, a y value that it goes through, and the slope that the function has. What's really nice about these types of problems, since y is not a function of x, they actually give you, in the setup for this problem, x1 and y1. So I know that the equation of my line is already going to be y equals m times the quantity of x plus 1 plus 2, because I'm already given x1 and y1. The only thing that I have to do, and it's a big ask, is to find what the slope is. And our slope is going to be dy dx evaluated at xy is equal to this point right here, -1, 2. All right, so it's going to be kind of difficult to get that, but once we get that, we good. So now, time to get there. And to get there, we're going to take the equation of the curve, and we are going to differentiate both sides. So I'm going to ddx, the side of x squared minus xy plus y squared, and I'm going to dx 7. Okay, right-hand side's going to be really easy. Usually I'm sarcastic about this part, and I say, ooh, this part's having... No, this part over here, the left side, is super-duper difficult. It is, yeah. It doesn't look that difficult, but really it is. I'm going to try to show some cautions that I have for you guys. First off, the derivative of x squared, that should be basic. You got 2x. The next part is the part that I see people screwing up all the time, because we have minus xy. And when we have xy, xy is a product of x and y. It is x times y, so we have to use the product rule. I cannot tell you how many people I have seen do this problem, and they say the derivative of xy is just y prime. No, we need to, with our product rule, left, I'm going to put these in parentheses because everything's going to have this minus applied to it. Left being x, the right, the d of the y is going to be 1 times dy dx. Add to it. We did left to right, now we have to do right to left. The d of x is just going to be 1. Alright, so everything inside those parentheses is the derivative of xy. Plus, the derivative of y squared is 2y times the derivative of y. Don't forget your chain, or else you get it wrong. Equals, and again, I usually am sarcastic at that point and say, here's the hard part. It is not. That's the easy part. The right-hand side, it's just 0. Now, we have to isolate the dy dx and get all the other stuff on the other side. So, in order to isolate, I'm going to distribute my minus. I'm going to have it as 2x minus x dy dx minus y plus 2y dy dx is equal to 0. And now you get to have some sort of freedom. Which one do you want to toss to the other side? Personally, I think adding y and subtracting 2x is going to be the easier way to do it. So, in my opinion, I would now have negative x dy dx plus 2y dy dx is equal to y minus 2x. Looking at the left-hand side, I can now factor out dy dx. So I'm going to have dy dx times the quantity of negative x plus 2y equals y minus 2x, or dy dx is equal to y minus 2x over negative x plus 2y. Again, my slope is going to be dy dx evaluated at negative 1, 2. So to find my slope, I'm going to evaluate at negative 1, 2. And just mashing this stuff in here. Y is 2, so 2 minus 2 times negative 1 over negative x, so negative 1 plus 2 times 2. Just looking at this, 4 fifths. Slope is 4 fifths. So now I know the tangent line is going to be y equals my slope 4 fifths times the quantity of x minus x1, which was negative 1. So x plus 1 plus y1, 2. My normal line, again, normal, just meaning that I have opposite and reciprocal slope is perpendicular to the tangent line. So I've got y is equal to opposite and reciprocal. Negative 5/4. Slope is the only thing that changes, so I keep the point the same. And boom. I've got the equation of my tangent and my normal. And what's really cool now, since I have Desmos already populated with all this stuff, I can actually graph the implicit function right over here and the tangent line and the normal line to see that I actually have the correct stuff right over here. Now, if you have a TI Inspire, I know will allow you to graph this on the calculator. However, those of us that have the TI-84s, you cannot graph this on your calculator. So you're just gonna have to rely on you doing the work right in order to check it like on a test or something. All right. I said, go to the next page. I said, go to the next page. I said, there we go. Higher order derivatives. Now here's where it gets kind of really kind of weird. When we're talking about second order derivatives, again, we're going to do lots of practice tomorrow as far as doing the first order derivatives. Hopefully we'll be able to do lots of practice with higher order derivatives. We know in order to find the second derivative, we first need to find the first derivative, right? So looking at this, I know to find the first derivative. You know what? I don't like putting it way over there. Let's slide over a little bit so that we have some more room to do this whole problem. So we're going to need a little bit of room. To find the first derivative, I'm going to ddx both sides. 2x cubed minus 3y squared, and I'm going to ddx the other side, right? Again, the concept of equality, if you do something to one side of an argument, you got to do the exact same thing to the other side of the argument. Looking here, the derivative of 2x cubed, since it is the x, we can just straight up take the derivative. We get 6x squared minus, here's where we have to actually use the chain, because we've got, bring the 2 down, we get 6y, but we actually have to remember dy dx. And looking on the other side's not too difficult. Derivative of 7, that's 0, right? Now we need to solve for dy dx. And when I'm solving for dy dx, I might subtract 6x squared from both sides. I get negative 6y dy dx is equal to negative 6x squared. Solving this, I'm going to divide by negative 6y. I see negative and negative cross out, 6 and 6 cross out. I've got dy dx is equal to x squared over y. There's my first derivative. Now for the fun part. The fun part is finding the second derivative. To find the second derivative, I need to take the derivative of the derivative. So I'm going to be taking the derivative of x squared over y. So d2y dx2. To find this, we see that we've got a fraction here. Again, fractions, we need to use the quotient rule. If you're still not using the quotient rule on fractions, you are doing it wrong. So here, I've got low d high, high d low, low low. So low y times the d high. D high derivative of x squared is 2x minus high d low. High being x squared, d low being the derivative of y with respect to x. So just dy dx. Of course, if this was y squared, we would have 2y dy dx, but since it's just y, it's just dy dx up there. All over low low, low squared. This is kind of the answer. It is not the final answer for anyone. You have to do at least one more step. Because technically, this is not an acceptable answer because I've still got dy dx in here. I need to sub in whatever dy dx is in order to make sure that this equation does not have any derivatives in the problem. So here, at the very least, I need to back sub this guy right up here. So at the very least, I mean, y times 2x, I could call that 2xy if I want to, minus, and at the very least, it needs to be x squared times x squared over y. all over y squared. At the very least, that's what I need to see from it. Now, that doesn't look great because I have fractions within fractions. In order to get those fractions out of there, I can change this divide by y squared into multiply by 1 over y squared. And again, this part is just cleaning stuff up. In this numerator, I'm going to have 2xy minus x squared times x squared gives me x to the 4th over y. Again, I see that this, I'm trying to subtract fractions where I don't have common denominators. So if I wanted to clean that up, I would have to multiply this by y over y. So something that I could have would be 1 over y squared times the quantity of 2xy times y is going to give me 2xy squared minus x to the 4th all over y. And if I wanted to do this problem entirely to how I personally, Mr. Wojciechowski, likes to do it, I would now multiply in that y squared by that y. And I would have 2xy squared minus x to the 4th all over y cubed. But I will tell you, this answer right here, if you leave it there, 100%. Leave it here, 100%. Any of these answers from this answer down are acceptable. All right? Did I get it right? Yeah, I got it right. Of course I got it right. There's also a little bit of an extra rule this chapter or this section, and that's really just the power rule with rational exponents. But we've done that before. Whenever we took the derivative of square root of x. So you'll have seen it before, but it's in your notes nonetheless. And that is a